Hello! So today we're going to talk about the pyruvate dehydrogenase complex and the most relevant reaction of the Krebs cycle. So it goes in 3 points: acetyl-CoA production, Krebs cycle intermediate, and Krebs cycle regulation. So enjoy! The conversion of pyruvate into acetyl-CoA happens in the mitochondrial matrix and especially in 3 subunits: E1, E2, and E3. The first step is a decarboxylation of pyruvate, which results in the production of an acetyl group and a molecule of CO2, which is the first product of the reaction. The acetyl group is bound to the TTP coenzyme, which is prosthetic. That means that TTP itself is covalently bound to subunit E1. In this scheme, all the prosthetic enzymes are represented in orange square. The enzymes that are not bound to subunits are represented in pink. Meanwhile, in E2, coenzyme lipolysin is reduced into its reduced form by accepting 2 electrons, and then the reduced form accepts the acetyl group from TTP and becomes acetylated. Lipolysin now carries 2 electrons and the acetyl group. The following reaction consists in giving the acetyl group to coenzyme A, and the result in the formation of the final product, acetyl-CoA. From now on, all the reactions that happens are for the recycling of lipolysin and FAT. As the acetylated form of lipolysin as giving the acetyl group to CoA, it remains the reduced form of lipolysin, which is going to transfer the 2 electrons to FAD. FAD is then going to be reduced into FADH2, and the reduced form of lipolysin oxidizes in lipolysin again and is now ready to begin again. The FADH2 is now going to give 2 electrons to NAD+, that is going to be reduced into NADH, which is the final product of the whole reaction. With all this reaction, we have recycled the FAD and lipolysin. So now let's talk about the Krebs cycle. So the first reaction of the Krebs cycle is the synthesis of citrates. So we have acetyl-CoA that come from the decarboxylation of pyruvate, that we saw before, plus oxaloacetate that through the catalyze of the enzyme citrate synthase is going to give citrates that has cis carbon. It's an exergonic reaction and it's irreversible. So the second reaction of the Krebs cycle is the isomerization by dehydration and rehydration of isocitrates. Citrates that we had before is very bad for oxidation, so it has to be rearranged into isocitrate. That is a good substrate for oxidation. Citrate is going to be dehydrated into cis-aconitate through the enzyme aconitase and going to be rehydrated through the enzyme aconitase into isocitrate. It's an endergonic reaction. So the third reaction of the Krebs cycle is the oxidative decarboxylation of isocitrate, the synthesis of alpha-ketoglutarate. So isocitrate is going to go through an oxidation that is going to be catalyzed by the enzyme isocitrate dehydrogenase. It means that it's going to lose its electrons and they are going to be carried by electron carriers, NAD+, that is going to become NADH. The first carbon lost by isocitrate is going to form CO2, and the 5 left are going to form alpha-ketoglutarate. It's an exergonic reaction, and it's regulated by the product inhibition and the ATP level. So the fourth reaction of the Krebs cycle is the oxidative decarboxylation of alpha-ketoglutarate, or the synthesis of succinyl-CoA. So alpha-ketoglutarate is going to go through an oxidation that is catalyzed by the alpha-ketoglutarate dehydrogenase complex that is identical to the pyruvate dehydrogenase complex. It's going to lose some electrons that are going to be carried by NAD+ and going to form NADH. So the second carbon loss is going to form CO2 that is going to be released in this reaction. And the 4 remaining carbons are going to form succinyl-CoA. CoA is an acceptor of the succinyl group, and succinyl-CoA is a strong bond, a C-ester bond, and so it's a really exergonic reaction. And this reaction is regulated by the product inhibition. So the fifth reaction of the Krebs cycle is substrate-level phosphorylation, or synthesis of succinate. So succinyl-CoA is going to be transformed in succinate through the enzyme succinyl-CoA synthase. This enzyme is going to be phosphorylated because succinyl-CoA can't, because it has histidine group. And what allows us to do so is the energy of the C-ester bond. So the phosphate is going to be bound to the succinyl-CoA synthase, but also to GDP, and that is going to form GTP. This GTP is going to allow us to produce ATP later on. This is a slightly thermodynamically favorable and reversible reaction, and the product concentration is always kept low, so the reaction can pull forward. So the three last reactions of the Krebs cycle are going to be reactions that are going to help recycle oxaloacetate. So the Krebs cycle can continue. So the sixth reaction is the succinate oxidation, or the synthesis of fumarate. So succinate is going to be transformed into fumarate, and the enzyme helping this process is succinate dehydrogenase. Succinate is going to go through an oxidation. It's going to lose its electrons, and it's going to be carried by FAD, that is going to become FADH2. This is a near equilibrium reaction, and it's reversible. The product concentrations are still kept low, so the reaction can pull forward. The seventh reaction is dehydration across the double bond from fumarate to L-malate. So fumarate is going to be transformed into carbanion transition state with the enzyme fumarase and through a gain of OH-. And carbanion transition state is going to be transformed into L-malate through the enzyme fumarase and through a gain of 1 proton. And so a slightly thermodynamically favorable reaction, and it's reversible. Still, the product concentration are kept low to pull the reaction forward. So the A step of the Krebs cycle is the oxidation of malate to oxaloacetate. L-malate is going to be transformed into oxaloacetate through oxidation, and it's helped by the enzyme malate dehydrogenase. L-malate is going to lose some electrons that are going to be taken by NAD+, that are going to form NADH, and so it's a very endergonic reaction, and it's irreversible, and oxaloacetate concentration is always kept low by citrate synthase, so the reaction can pull forward. It's the last step of the Krebs cycle, and it's going to allow a new cycle to start. The regulation of citric acid cycle happens when there is too much energy or not enough produced. So the reactions that are going to be regulated are the pyruvate dehydrogenase complex, the citrate synthase, the isocitrate dehydrogenase enzyme, and the alpha ketoglutarate dehydrogenase complex. The citric acid cycle is going to be activated when there is a substrate availability, when the ratio of NADH over NAD plus show that there is more NAD plus than NADH, so no more energy, when the ratio of ATP over ADP show that there is more ADP than ATP, no more energy, when there is an activity signal, like an increase in the muscular concentration of Ca2 plus. The citric acid is going to be inhibited when there is a product accumulation, when the ratio of NADH over NAD plus shows there is more NADH than NAD, too much energy, or when the ratio of ATP over ADP shows there is more ATP than ADP, too much energy.